Okay, so now we had started learning about instrumentation amplifier, right? So in instrumentation amplifier, this is actually a huge circuit altogether, and we had broken up this huge circuit into smaller pieces, right? And the first section, that we learned about, is the differential input output amplifier. So this has a differential um, output voltage stage, right? So how do I say that it has a differential output voltage stage, right? We have op-amp A1 and then A2, right? So this is the gain of op-amp 1 and the gain of op-amp 2, right? A2. And we also saw with different combinations here, right? uh, where I can just give one voltage, right? So we have seen that in different section, right? So that was common mode, right? Okay, so we learned about the common mode type. Let me just show you that as well. Differential, we were giving different voltages here, V1, V2, and then we try to combine them both. Yeah, it's here. So we try to combine them both and give a common potential. Okay, so you can understand here that this instrumentation amplifier, okay, is not just a simple amplifier, but then it has two types of circuitries, right? So in the first stage, I do have it's broken up into the differential circuit, and then I have the difference amplifier, right? So there are two different things here. So we have seen here how this holds good, right? Where we have voltage V1 given with respect to ground, and voltage V2 given here to op-amp 2 with respect to ground. Okay, right. And this was the major resistor here, right? So we were seeing that this resistor is actually playing a very major role in controlling the levels of outputs between both of the resistors, right? So that's important. And we were also looking at resistors R1 and R3, right? So how these resistors are inside the feedback, and since they are in the feedback, right? So we also saw that since this is connected, the junction between R2 and R3 is this point. So we were seeing that R2 has actually a major role here, so which means I can make it a kind of variable resistance, right? So when I make it a variable resistance, and then I can actually change the way the output response, right? So if I want a higher potential, or if in case the gains are not working out fine, then maybe I can reduce the resistance. So all this is possible, having a separate resistance here, but then I cannot do that here. I would not wish to do that here with R1 and R3, right? So I will try to do that here with R2 alone. Fine. So these were some of the concepts that we saw in our previous class. The differential input output, how it's important, and we also came across few equations, right? So the important equation here that we saw is the output voltage, right, being R1, R2, R3, right, the sum of all, and then dividing by R2. So this is an important formula, right, where I can control my output voltage V0, and this control is happening with the help of majority, which is taken care by R2. Fine. Okay. So not only this kind of differential inputs, when I say differential, giving different type of inputs, V1 is different, V2 is different, right? So not only that, we even try to combine these, input terminals together and then give it a common input voltage. We have seen even that. So we saw that the differential closed loop gain is V naught output by input, which is R1, R2, R3 divided by R2, right? So usually what we do is we take this R1 and R3 to be common. That's because I want these op amps to be as identical as possible. Okay, I do not want to have different types of outputs coming in from op amp 1 and op amp 2, right? I want identical outputs. So usually I will not play around with R1 and R3, but then I try to keep it as constant as possible. Okay, fine. So here, okay, since we equate it with R1, we equate R3 with R1, so obviously it's going to add up, right? So which means I'm going to have 2 times of R1 plus R2. So R2 is a separate, you can see, it's a unique resistor here, right? But then I'm able to add, R1 and R3. So it's like, I'm assuming these resistors are the same, R1 and R3. So it's like R1 plus R1. So I'm able to get 2 times of R1 here, right? And R2 is remaining, right? Plus R2 and divided by R2. So I cannot actually, cancel them out because it's an additive factor here and it's a division here. I cannot do that, right? So this becomes my differential closed loop gain, which is 2 times of R1 plus R2 divided by R2. Okay. Right. And we also try to combine them both, right? When I say combine, which means I'm giving a common input. So this is also referred to as common mode input. So the specialty here is, I'm going to get everything as Vn. So whatever voltage I'm giving here, right, across my op amp, okay, so that becomes my output as well. No matter I check at this point or probably here or probably with respect to R2 and ground and then R1, right? So I'm going to get the same level of voltages. Okay, so that was the beauty here. And we were able to see that the closed loop gain is equal to 1. Okay, closed loop gain was equal to 1. And common mode signals will be passed through but not amplified by the differential input-output amplifier. So here, okay, in common mode gain, so whatever signal you are giving, the same you are receiving. So which means there is no any kind of amplification process happening, right? So it's just passing of signals from one point to another, from the input side to the output side. Okay, fine. Then we try to combine them, right? We broke those circuits separately. So we saw these, we studied about this differential circuit, and then we studied about this difference, and we try to combine them, right? So we were able to see that, the RI1, okay, so this one is equal to R1 at input terminal 1, and RI2, okay, is equal to R3 plus R4. Okay, R4 is here and R3 is here. So this circuit is going to come and sit here. Okay, so you can see this dotted line which differentiates the difference and the differential amplifier. So both are connected. So the output of first stage is actually going as inputs to the second stage. Right. So consequently, you can see currents I4 and I6 getting generated. Okay, so we were able to have a variable resistance for R2, right? So in our complete instrumentation amplifier. R2 I made it variable, and R7 also I made it variable. R7 I made it variable so that whatever effects, the bias effects because of the stage 1, that can be counterattacked with the help of this resistance. Okay, fine. And one more thing that we actually saw was most loads have one grounded terminal. Okay, the grounded terminal concept also we learned. Otherwise, ground loops and static electricity could cause problems. So we had discussed this in our previous class, right? How static electricity, I had given the example of a computer and constantly connected power supply cord. So this happens for if it's just left unattended for a long time. Okay, right. So we came up with equations. ACL is equal to ACL1 into ACL2, where this ACL1 is actually referring to stage 1 and ACL2 is referring to stage 2. Right? So it's a combined effect. So excuse me, if I can change the gain of one of the stages, right? So it is going to impact the overall gain of my instrumentation amplifier. Okay, and you can hear, you can see that the gain can be adjusted with R2. Right. So today we will look at a few examples, right? So based on these equations, I want all of you to be ready with your calculators, pens and notebooks, so that we'll start working on these problems. So the question says, design an instrumentation amplifier shown in the figure, right? So we are referring to the same final instrumentation amplifier that we have right now with the stage 1 and stage 2, right? So we're going to design that with the help of op-amps. So all these are op-amps, A1, A2, A3. So 750 nano amps is going to be the maximum input bias current. So which means I got I bias, right? I got the value of I bias, which is about 750 nanoamps. So the circuit is to produce an output ranging from 4 to 8 volts. So which means this is going to be my V0. Okay, V0 can be ranging from 4 to 8. And the input is 10 to 20 millivolts. Okay, so input, output, and the bias currents. So we will take it step by step, stage 1 and then stage 2. So design stage 1 to produce all of the voltage gain, and stage 2 to have a gain of 1. Okay, remember I had told you ACL is going to be equal to 1, right? Okay. Now I2, okay, as we usually do is we take 100 times the IB max. So IB max here is already given to us, which is 750. Okay, and then I multiply it with 100. So just cross check, are we getting 75 micro?
Getting, sir.
Getting it? Okay, good. So 75 micro is fine. So we are okay with this value. And then R2, okay, R2, resistor 2. Now where is my resistor 2? This is a special resistor, as I told you, right? Which is actually variable. So I take the minimum input voltage. Okay, so I'm not taking 20 volts or 20 millivolts, but then I'm taking 10 millivolts. So 10 is here, and the I2 current, okay, I2 which is calculated as 75 micro. Please divide and see if it's fine. 10 divided by 10 milli divided by 75 micro. Are we getting? How much are we getting? It's 267 coming. You can work it out. So simple division.
Sir, I'm getting 133.
133, right? That is because the minimum voltage is taken. So if we take 20, try with 20, you should get 267. We have to replace this with 20. Millivolts. Getting it?
Yes, sir.
So we will take 20 millivolts here, and the maximum input voltage. And if we take 10, then we are going to get about 133.33, right? If I'm not mistaken. And here it's going to be 266.66. So we're going to round it off to 67. I do not have a standard value of 267, so I'll increase 3 ohms, and I'm going to take a 270 ohm resistor. Okay, so we're fine with this now. 270, right? Now let us go to the output voltage. Now they have told us output, is ranging from 4 to 8, right? So we're going to take V0 is equal to 4 volts, and VR1 is equal to, so voltage across VR1 is equal to 2 volts, and voltage across VR3 is going to be 2 volts, right? Because it's differentiated, okay? And so R1 is equal to R3. So if in case R1 is equal to R3, then I have VR1 divided by the I2, whatever current that is passing through, right? So this I2 that you can see here, I'm going to divide by that minimum value. So VR1 and VR3 is the same. So we are going to have 2 divided by 75 micro. Are these values proper? 26.6. 2 divided by 75 micro.
Getting.
You're getting it, right? Okay, good. So we will round it off here, probably about another 0.4 kilo ohms, right? So we'll make it 27, and yeah, when V0 is equal to 4 volts for first stage, okay, VC, okay, voltage at point C. So you can see here, right? There is, in small you have A, B, C, D, E, F. Okay, then G, H, I. Okay, so there are at different points. Okay, it's named here. So we will go with voltage at point C, okay, is going to be plus 2 volts, and voltage at point F, okay, is going to be minus 2 volts. If we are considering this 4 volts, so VR6, okay, so VR6 is going to be uh, across resistor R6, okay. So we are going to find the voltage across R6, right? So VR6 is equal to VR7, okay. So this is also equal to 1 volt. So how are we getting this? This is voltage divider, isn't it? So we're going to get VR6 and VR7 is equal to 1 volt because we have 2 volts here. Okay, fine. And now we'll go to R6. I want to find out the value of R6. So what is going to be the resistance? So VR6, I have the voltages here, right? 1 volt. And I2 minimum, we have it from here, 75. So 1 divided by 75. So is it fine? 1 divided by 75 micro. Yeah, we're getting that value, 13.3K.
Yes, sir.
Okay, good. So R6 is here. So we're going to use a 12K resistor. Now for the second stage, right? Now we're going to concentrate on stage 2. For second stage to have gain of 1, okay. So we need to have all of the resistances to be equal, okay. So I will have R4, then R5, R6, okay. R6 is anyway calculated, R7, okay, all to be equal 12 kilo ohms. So only when there's going to be equal resistances, and I'm going to have a gain of 1. So which means if I can just find out one resistance here, I can put these resistance values to the others as well, right? So this is the importance of studying problems. You will be able to design circuits. If in case an instrumentation amplifier, if you have to rig it up in your breadboard, or probably if you have to simulate it, okay, you can find that you know calculating these values individually, right, will be able to uh, take equivalent resistances. Like for example, here I have 26.6, I'll be taking 27, right? So you can actually give your inputs and check the outputs. You can also check for common mode inputs. If you're giving 5 volts, then are you getting 5 volts? So all these are interesting. You can if you do not have access to these resistances, you can anyway simulate it, right? There are various circuits which enables us in simulating and seeing the outputs, right? So only when you do that, your understanding will still go deeper, okay. Remember, we used to do some computer based circuit analysis, right? So in that also we were getting standard forms of values, right? So we were able to compare the practicality values and then the theoretical values. So computer helps us analyze and get almost the nearing values. Okay, so we are going to stick with keeping all the resistances for having a gain of 1, okay. ACL is equal to 1. So all of these resistances are going to be put as 12 kilo ohms. Okay, so was there any doubt in this problem that we saw? Any doubts with this problem?
Sir, R2, I have getting
R2 in which
two
section? Here,
R2, sir.
initially,
I getting kilo ohm.
R2, 20 milli divided by, for that value.
Yes, sir.
Okay, let me also just check. 20 milli divided by 75 micro. No, you are getting 266, only 266. There's no kilo there. Try again. Use 20 milli, or you can even take 75 micro, take it as an inverse and multiply with 20 milli. 20 into 10 raised to minus 3. You can do into 10 raised to minus 3, or your calculator already has milli. You can just use that.
Yes, sir. Yes, sir. Getting.
Fine. So yeah.
Yes, sir.
So in this way, we take step by step, and then first we calculate the currents, and then from the current, I know the input voltage. So I'll calculate the resistance, because R2 is major for me. Once I know R2, then it becomes R2 and I2. I have solved most of the problems here with my circuit. Okay, and voltages are already given here, so I'm going to use the same thing. Okay, so I'm going to divide them, and I'm going to use equivalent. So those concepts, few tricks and techniques you have to remember, right? So like how these two are becoming 2 volts, and why is it +2 and -2, right? So that's because of its very nature here, right? It's very nature. Okay. So now we'll move on to the next problem, okay, the next example. Right. So we'll calculate the voltage gain for the instrument, same circuit, right? So what all we saw previously for the same circuit, now we are going to have slight modifications. So calculate the overall voltage gain. So now they're asking us to calculate A. Previously, we dealt only with R, I values, right? So now we are going to deal with the gains as well. Calculate the overall voltage gain for the instrumentation amplifier. Okay, so just read that. Okay. Meanwhile, please make a note of the formula. So the important formula here is going to be ACL. Remember, we just discussed about it 2 times R1, right, plus R2 divided by R2. So this is the main formula whenever we talk about gain, right? So now let's extract data from the question. Calculate the overall gain for the instrumentation amplifier shown in the figure here. Also determine the DC voltage levels throughout the circuit when the input at terminals A and B is respectively plus and minus 10 millivolts respectively. So I having the first flow here, which is 10 millivolts at terminals A and B. Okay, so A and B will have plus 10 and minus 10. See, I have minus here, I have plus here, so that's why it's called differential inputs. And 1 volt common mode input is present. Okay, so this is a little bit tricky. Now we're going to have 1 volt as common mode input, and we're going to also calculate for 10 millivolts and plus 10 and minus 10 millivolts. And what are we to calculate? We have to calculate the gain, the overall gain. Also determine, we need to find out the voltage, DC voltage levels also at the input terminals. Okay, also determine the DC voltage levels throughout the circuit, right? So voltage gain, number 1. Okay, number 2, DC voltage levels, and then I know that the inputs are going to be plus 10 and minus 10, and I'm going to do it for another case where common mode is going to be 1 mole. So very interesting problem. So we will try to solve it step by step, and we'll try and understand how to design this amplifier. So first things first, we'll take the formula ACL, right? So ACL is a very important formula for us. So we take 2 times R1 plus R2 divided by R2. So 2 times R1. R1 I have already calculated, isn't it? So that's about 27, right? 27 kilo ohms. I already have it here, and plus 270. 270 we calculated previously, right? R1 and R3 we had used the formula R1 is equal to R3, and we had calculated. So 270, please check, students, are we getting 201? Either you can first calculate the numerator part and then just divide by 270, or the reverse way also is fine, no problem. So first you can multiply 2 and 27, right? So that will give you 5400. No, 54,000, sorry. 54000. And after that you can add 270 to it. Right, so that should be giving you about 54270, and then divide the value with 270. Are we getting this 201, students? Yes, are we getting those values? 201. Very simple calculation, right?
Yes, sir.
Okay, fine. So 201 is fine for us. So we'll continue with since we have got ACL1, right? So for the first stage, and now we'll continue with the second stage, right? ACL2. Right. So voltage gain, DC voltage, inputs 10 millivolts, 1 mole common. Fine. So we have ACL1, right? Now ACL2. So ACL2 now is very much dependent on this feedback, which is R5 divided by R4. Okay, so the input that comes across. So here, I have just the same value. That's the reason we kept all the resistors same, so that if I divide the numerator and denominator, I just get 1. Okay. So ACL is equal to ACL1 into ACL2. So 201 into 1. Okay. So that should give me about the same value. Fine. So it's nullified, right? So numerator and denominator gets cancelled. It's just nullified. Voltage at even in non-inverting input terminal, that is terminal A, right? So where is terminal A? Here, non-inverting, right? So we're looking at op amp 1 in stage 1. Is VA is equal to VN. Okay, so VN is here. Okay, now VN is actually 1 that we have given, right? So the question told us that along with this, there is a 1 volt common mode input also. Okay, so VA becomes VN plus VI. So VI, okay, here is about 10 millivolts, right? We're giving plus 10 millivolts, and it has 1 volt common. So I add them together. So I should be getting about 1.9 0.01 volt, right? So it's a combination. It's a combination of the input that you're giving here, okay, and the common mode input. So you have to add them together. So once you add, it becomes 1.01. Voltage at even in inverting input terminal, right? So which is terminal D, okay? So terminal D is here, okay? Is VD is equal to VA, okay? Is equal to 1.01. Can someone now tell me how come I can equate it with the same values? How can VD be equal to VA? How is it same? 1.01 volt. See, VD is here, right? And VA is here. How is it same? Recall the concepts that we have studied so far. What is the property of an op-amp? Yes, can I have some response? What's happening? Why is VD equal to VA? Because that's the very property of an op-amp, right? So whatever potential is here in the non-inverting terminal, the same potential will try to be replicated in the inverting terminal. So this is connected here, isn't it? This is connected here to the op-amp. So which means both the voltages should be the same. So I'm going to have VA, VD both 1.0. Right. Now voltage at A2, the second one. So we are taking here minus 10, remember, here plus 10 and minus 10. So minus 10 and 1 volt. So, that's going to give me about 0.99 volts. Okay, so less than a volt. So voltage at A2 inverting input terminal. So which means, I'm going to take the same concept here. Okay, E, okay, D is here and E is here. So at E also it becomes 0.99 volts. Any doubts here, students? Can I proceed? Is it fine?
Yes, sir.
Okay. So you should remember, why these voltages are becoming same. Okay, all these concepts you should remember. We have studied this, right, previously. Fine. So we have this one now. So we'll continue. I've brought forward the same figure here. Okay, so it becomes easy for us. So current through R1, R2, and R3. Now we have to find out how much of current to R1, R2, and R3 is passing. So we know that, I2 is equal to VR2, okay, voltage across that particular resistor, okay, and the value of the resistance. So VR2, okay, the voltage, since I have 2 points here, so VD minus VE, because it's potential difference, isn't it? It's potential. So I minus them both, okay, so 1 minus just a moment. So I minus them both, right? So once I minus, then what's going to happen? 1.01 divided by minus 0.99 divided by 270. R2 was already calculated. So can you please check if that's the value? 74.1 micro. Yes, no, please respond. See, simple 1.01 minus 0.99. We're going to have some value. Okay, so that's about 0.02. Divide that by 270, right? So are we getting this value, students? Please respond.
Yes, sir.
Okay, so we are actually getting about 74.07, right? 074. So I approximated to 74.1 micro. Okay, so voltage A1, voltage at A1 output terminal, that is terminal C. Okay, terminal C is VC is equal to VD plus, okay, whatever potential is at VD plus I2 into R1. Okay, so I2 we know, and whatever is the multiplication or the product value of I2 and R1. So this is going to be 1.01 BD. We know because this is also 1.01. Okay, plus I2, we have calculated it as 74.1 into R1. R1 value is already 27. Okay, so you can first multiply this, which is in the bracket, 74.1 micro into 27K. Okay, so you will be getting about 20,007. So you can, sorry, 2.007, and you can add it with 1.01, right? So approximately 3 volts. Is it proper? Yeah. Is it fine?
Yes, sir.
Okay, good. So this value is also fine. Okay. So next, now we will see voltage at A2. Okay, so this op-amp here, voltage at A2 output terminal. Okay, which is uh, F. Okay, the terminal F. So VF is equal to VE. Okay, the same concept what we have here. Okay, VE minus I2 into R3. Okay, I2 into R3. So whatever is my uh, product. So I'm going to have 0.99, okay, minus 74.1 into 27. So we should be getting about 1.01, minus 1.01. So once I calculate both of the output voltages at A1 and A2, right? So the next is I'm going to go with the next op-amp, which is A3. Okay, so I need to find out what is VH. Okay, and then I find out, once I find out VH, that's going to be equal to VG, and once I have this inputs, then obviously it's going to be easy for me to calculate the output, because the resistance value is anyway known to me, and the load value is also known to me, right? So VH is equal to, okay, voltage at point. Okay, so that's VF, right? So this is actually coming here, right? So this voltage through the resistance, and into R7, okay, into R7 divided by R6 plus R7. Remember, I had told you this is voltage divider, right? So we get these values, and we just get about minus 0.505. Let us just calculate minus 1.01 into 12 divided by 24K. Yeah, are we getting those values? Minus 0.505. Yeah. Okay. So similarly now voltage at A3 inverting terminal. Okay, so this is also going to be the same. Okay, minus 0.505, and then now I calculate the voltage across R4. Okay, so that is VR4 is equal to VC. Okay, because it's coming from here, VC value is known to me, minus VG. So two potentials I'm minusing. Okay, so I will know what is my exact voltage across R4. So I have 3.01 pre-calculated and this minus 0.505. So once I minus them, right, so I will be getting, so minus minus it becomes plus, so 3 plus half, so it's about 3.5. So the current through R4 and R5, so I'm going to calculate I4. I4 is equal to voltage across R4, okay, divided by R4. So this is 3.52, R4 value is 12, right? So let's do a quick math here. 3.52 divided by 12K, right? So yeah, if we take the standard value, then yeah, 293 micro. So the output voltage now, since I know all these voltages, intermediate voltages, V naught is equal to output voltage, V naught is equal to VG. Okay, so VG is here, VG minus VR5, because this is connected, isn't it? So minus VR5 across resistor R5. So minus 0.505 and minus, okay, 3.55, just bring it down. Okay, so I should be getting about minus 4 volts. Okay, minus 4 volts. So in this way, you know, we take it step by step. We you know, calculate one value and then pass on to the next stage. And once we know the resistor values, we can obviously find out the current values as well. Okay. So any doubts here, students? Is it all fine? You have to go through it again. Okay, so go through it again, you'll be able to understand in a much better way. You have to solve it. Okay.